Hey everybody, this is Bharat Muthuswamy.
And Amir Muqtadari. In this lab, we will study how operational amplifiers can be configured to produce other amplifiers that has large input impedance and high noise rejection. Let's get started.
Okay, we will analyze the circuit shown here. This circuit is composed actually of three operational amplifiers and is called as the instrumentation amplifier. Instead of understanding the problem, because the analysis is pretty straightforward, let us understand why instrumentation amplifier.
So, is it a differential amplifier that is augmented with input buffers?
Correct. And because of the input buffers, the instrumentation amplifier has very high input impedance, making it ideal for interfacing with circuits that have very low output impedance. A specific example is electrodes for electroencephalogram.
I also see that because the instrumentation amplifier is basically a differential amplifier but with a higher input impedance, it can reject the common voltages at the inputs better.
Correct. The CMRR, or common mode rejection ratio, is very high.
Now that I understand why we use instrumentation amplifiers, let us devise a plan to solve for Vout. The plan is simple enough. Use op-amp golden rules in theoretical analysis. Use simulation and physical realization to understand non-ideal behavior.
Correct, but one item I would like to point out is practical instrumentation amplifiers come as a single package. The three op-amps are built in. The reason is to get very good performance, you need the resistors, especially R1s, to be precisely matched, and this is usually done by laser trimming.
Okay, now for the circuit analysis, using the op-amp golden rules. For the differential amplifier, we simply have the expression shown.
Correct, Amir, that's excellent. Notice how Amir has started his solution by subdividing the circuit into different sub-circuits. This is a very useful technique, that is, you simplify a complex problem into simpler pieces. As a reward for Amir, I'll finish the rest of the analysis. Okay, so we'll apply Kirchhoff's current law at this node labeled V1 and also Ohm's law. So the current flowing through R1 from top to bottom is given by VO1 minus V1 over R1, and that's equal to the current flowing through the R gain resistor, because there is no current flowing into the inverting terminal of U1A op-amp. So the current through R gain is given by V1 minus V2 divided by R gain, and that's our KCL expression. But this same current flows through the 1 kilo ohm resistor connected to U1B. And if you write that expression, that's shown right here. Now, from these two expressions, we will eliminate VO2 and VO1 because the question is asking us to find Vout as a function of V1 and V2. So eliminating VO2 and VO1, which is through basic math, we get Vout as this expression, which looks complicated. However, if you notice, we can basically factor out a V2 minus V1. First, we will factor out a negative sign from V1 minus V2 here, and we will finally get Vout as R3 over R2 times 1 plus 2R1 over R gain times V2 minus V1. Notice the expression on the right-hand side has units of volts because the gain is obviously dimensionless. And for the resistor values we have shown here, we get a gain value of 3 because R3 equals R2, so the gain here is 1. R1 equals R gain, so you just get 1 plus 2 as the simplification of 1 plus 2 R1 over R gain, and that's equal to 3. All right, now for the multi-sim simulation and the lab demo. I'll do the multi-sim simulation. Amir is setting up the circuit right now for the lab demo. Okay, so here is my circuit, which I've set up already in multi-sim. Some points to note. I have 3 TLC 277s, but 2 of them, U1A and U1B, are from the same package in multi-sim. So when I power up one op-amp in the same package, notice how the rails on the other op-amp are already automatically connected. I put in 0.5 volts to V1. V2 is grounded, so the output I should get is approximately 3 times 0.5, or 3 times 0.5, but it's V2 minus V1, and since V2 is grounded, I'll basically get an output of negative 1.5 volts, and that is what I see here. Pretty straightforward. Now, one thing I want to point out while you have when you have a multiple op-amp circuit is that it is possible that depending on your values for R1 or gain, that your input op-amps might rail, before the output op-amp. And in that case, the system is not linear. So in other words, you should always check that all your op-amps are in the linear region of operation.
So this is our instrumentation amplifier lab demo. As you can see, we are using two TLC 277 op amps. Each of those TLC 277s has 2 op amps built in. So we're currently using a total of 3 op amps to build this instrumentation amplifier. Over here, we're using our DC power supply to both provide positive 5 volts and negative 5 volts to the rails of the op amp. We're also using our 6 volt output to input 0.5 volts into the V1 terminal of the op amp, and we have grounded the V2 terminal. Over here on our multimeter, we see that we do have the gain of 3. We had a 0.5 volts, and we're getting a gain of actually negative 3, because if you do the equation, we have one side grounded and the other side at 0.5 volts, so it's 0 minus 0.5, which is negative 0.5, times 3, which gives us negative 1.5 volts.
Okay, now that we're done with the simulation and the lab demo, it's time to work on the EX40 lab. Next time, we'll look at the Schmidt trigger and positive feedback. The analysis is probably something you've never seen before.
I'm really excited.
All right, see you then.